Now let us discuss particle injections and what does it mean, and what we have to do in order to define a particle injection. Now whenever we use discrete phase model within this commercial software Fluent, the discrete phase is in the form of particles which are tracked by Lagrangian method. The particles of the discrete phase should enter our domain of calculations from somewhere. In order to set their initial conditions and how they enter in our domain, we have to define injections. The particle enter into the domain through the way of injections. Various forms of injections can be defined which are closer to our physical real condition of the physics or problem that we are solving. Various particle injections can be defined which are very close to what exists in reality, how our instrument or equipment work. In order to define injections, we have to define particle position, that is, what is the initial or starting position of the particles, what are its x, y or z coordinates. We have to define particle velocity. What is the starting velocity of the particle when it enters the domain of calculations, what is its direction, what is its magnitude. We also have to define particle size, that is, diameter for spherical particles. What is the diameter of the particles or discrete phase that is entering into the domain. If we don't have spherical particles or don't have a exact diameter, we may use representative diameters to approximate the physics that we are modeling. We also have to define what is the initial particle temperature. In reality, when there is injection of particles or discrete phase, it is usually in the form of grouped streams of particles rather than individual particles. So in order to define such streams, we have to define the mass flow rate of the particle stream. For transient cases or unsteady problems, we also have to define particle start time and stop time. That is, when the particle starts entering into the domain and when do they stop, or where do they stop. Now let us see how these injections are given. There are two ways in which we can specify Lagrangian particle injections. Direct specification of starting conditions, that is, we directly indicate the starting conditions of the particle that is coming into the domain. We manually specify the particle positions, velocity, size, mass flow rate, etc. That is, we directly give the inputs and those values are used in order to define the particle injections or initial conditions. Second option is automated computation of starting conditions. This is suitable for standard equipments like atomizers and other standard injection equipments. Fluent calculates particle parameters based on automation submodels for standard injection devices. For general industrial purpose, various automation techniques are used in standard injection devices that are used in various chemical and mechanical industries. In order to replicate the physics of such injection devices, automation submodels are developed, and we can give those automation submodels in order to automatically define the injection device physics. What we need to do is identify which type of injection device that we are trying to model and then select the submodel which is closest to that injection device. First, let us see types of direct specifications. Within direct specification, the first type that we have is single. That is, a single particle enters the domain, we give its velocity, location, position, size, mass flow rate, etc. Second type is group. Within the group particle injection, streams of particles enters and we have to give the starting particle position, size, velocity for the first particle and the last particle. From those inputs, the entire stream properties are calculated and a group injection is carried out. This is the type of injection that we are talking about. We give the starting particle parameters and the last particle parameters, and all the particles in between. The entire stream is calculated by Fluent, and then stream of particles are injected. Next type is hollow cone, in which particles are injected in conical directions. This is the type of representation of hollow cone type of injection. We will study in detail all the user inputs required for such type of injection in future slides. Next is surface injections, in which particles are injected along the surface, which is this type of injections. Again, we will see all the inputs required for such injection in coming slides. We can also set up a file injection in which we give the parameters of all the particles within a injection file which we upload into the Fluent calculations. Another type is solid cone type of injection. In solid cone, it randomizes the particles in order to reduce grid dependency. That is, particle parameters are randomized and they can work on any type of grid. Even if we change the mesh for that particular problem, these solid cone injections will work on that. Specification of streams is required for such type of solid cone injections, and sufficient number of streams should be specified. Particle properties are randomized. Now, what is meant by this is, it is a truly random distribution of variables. Velocity, direction, and location are distributed in a random manner. That is, any particle stream can have any velocity, direction, or location. It represents a truly random injection in the form of solid cone. Now, when we use automated injections, let us see what inputs we need to specify as users and what parameters are calculated automatically by Fluent. Now, information that users have to specify is location, temperature, starting time, and information about the injector device. Whereas the size distribution and velocity distribution is calculated by Fluent automatically. That is, which particle will have what size and which particle will have what velocity is automatically calculated by using this various distribution models or automation models. Types of auto injection models that are available are plain orifice atomizer, pressure swirl atomizer, air blast atomizer, flat fan atomizer, and effervescent atomizer. All these submodels we will study in the coming slides. Let us now discuss what all particle types are available when we use the DPM model. We will see the particle type, then explanation of what the particle type means and what properties does it have, and then we will see what physical laws are applicable if we use that type of particle. First, let us discuss the massless particle type. This massless particle just follows the flow and temperature field of the continuous phase. It has no mass, it has no physical properties, and there is no force exerted on this type of particles. So basically, it is just a pictorial representation where the DPM particles are nothing but path lines and we are solving continuous phase flow. Now, what laws are applicable for such type of particles? Basically, there are no laws that are applicable because it is a massless particle without any properties and no forces are exerted on it. So, no laws are applicable, but if we want to include some type of physics, we can always give the user-defined law by UDF. Second type is inert particle. These are particles like droplets, bubbles, or particle-shaped discrete phase entities. In terms of laws, force balance is applicable on these type of particles. Also, inert heating or cooling can be applied. Third type that we will discuss is droplet particles. These are liquid, and these are liquid droplets in a continuous phase flow. Particle force balance is applicable to this. Also, inert heating and cooling laws are applicable. Also, we can model vaporization and boiling. Next type is the combusting particles. These are solid particles. They have physical and chemical properties. They are generally used for modeling combustion of particle. In terms of laws, particle force balance is applicable. We can also model heterogeneous surface reactions. This type is particularly used for such type of heterogeneous surface reactions which take place on particles. The non-volatile portion, that is the portion which does not combust, is also subject to inert heating law. And the last type that we can have is multi-component particles, which is basically mixture of droplet particles. If we have a type of mixture of particles in its type, we can include this particular multi-component particles. Multi-component laws are applicable and it integrates all processes of relevance in one equation. Let us discuss all the injection types in detail one by one. We will see brief overview of those injection types, what do they mean and how to apply them, and various user inputs that we give within the injection panel. First type is the single injection. As you can see in this picture, it is just a point injection. It is just a single injection given from a point. We can specify the point and a single stream of particle will be coming from that. There is no size distribution available. Only a single particle is calculated. Now we will see what all parameters or user inputs that we have to give in order to set up single injection. First user input that we have to give is position. As you can see, this is the set injection properties panel that we can obtain after clicking injections within the DPM model. Here we can give the x, y and z positions of injected stream along the Cartesian axis. So within the point injection within the single injection type, here we can give the x position, y position and z position in order. This will define the position of the point from which the particle will be injected. Second is velocity. As you can see here, we need to give the three components of velocity in the x, y and z direction. This will be the initial velocity with which the particle will be injected. Next is diameter. We have to give the diameter of the particle that is to be injected here. Next property that we have to specify is temperature. Temperature can be specified here within the set injection properties panel. This will be the initial absolute temperature of the injected particle stream. Next property is the mass flow rate. We can specify the mass flow rate of the particle. This is for coupled phase calculations only. And if we are solving unsteady flow or unsteady particle tracking, we have to set the start time and end time of the injections within the start time and the end time field, which appears if we have activated the unsteady particle tracking.